We're going to consider what happens to probability amplitudes, or more generally wave functions, when we have more than one particle in the system. This becomes interesting because of the fact that the measured quantity is the probability of finding a particle. But this comes from the square of the wave function or probability amplitude, and therefore there are two possibilities. One could put a -1 in front of the wave function, square it, and get the same result as not putting a -1 in front of the wave function. So we could have to consider both these probabilities. We'll look at the consequence of these two alternatives using scattering experiments in the center of mass frame introduced in the last module. There are in fact two types of particles corresponding to these two choices of putting a plus sign in front of the wave functions when you add them, or a minus sign. The minus sign case corresponds to particles we call fermions, whereas particles we call bosons require the plus sign. So now let's go back to our scattering experiment in the center of mass. Quantum mechanics introduces no complications at all if the physics of the scattering process lets us determine precisely what happened and which particle went where. This is the case for distinguishable particles. Now, I've shown you the center of mass scattering here for some arbitrary angle, but we're going to simplify things by considering scattering at 90 degrees in the center of mass frame of reference. The reason then being that the probability amplitudes for each of the two possible paths become identical, and so it illustrates the physics very clearly when this angle here is pi over 2. Now, if we have some way of labeling the particles, and we're going to consider that we can, say, measure their spin. We'll talk a little bit more about the idea of spin a little later. Then the situation is very simple, because, for example, if we have the situation on the left, particle 1 goes into D1, by making D1 the detector sensitive to spin, and say imagine that spin is clockwise on this particle, anti-clockwise on this, if this particle says I just measured a clockwise spin, it means P1 went into D1, and that means P2 had to go into D2. So in that case, these two are completely distinguishable, and so to find a particle, for example, in detector 1, to find the probability that a particle ended up in detector 1, we would simply add the probability, i.e. the square for scattering particle 1 scattering into D1, plus the square of the probability amplitude for particle 1 scattering into D2, we just add them together. So at 90 degrees, this just gives twice the probability of any one particle scattering at 90 degrees, because there are two particles. So this is a simple classical result. Particle 1 or particle 2 could have gone into detector 1. However, quantum mechanics kicks in with some strange stuff if the particles are identical. So let's look again at this diagram and now make the particles spinless, or have the same spin so we can't tell which particle goes into which detector. They're not labeled in any way. We have two entirely equivalent situations here. Particle 1 going into D1 or particle 1 going into D2. We cannot tell whether the diagram on the left or the right applied because we have no physical way of measuring it. Quantum mechanics says, well, if we have two paths that we cannot distinguish, we have to add the probability amplitudes together and square them. So let's go ahead and do this, and let's take the case of scattering at 90 degrees. Then the probability of finding a particle in detector 1 will just be given by the probability amplitude that particle 1 scattered into the detector, plus or minus the probability amplitude that particle 2 scattered into the detector, and then we will square all of that. In the case of bosons, we take the plus sign, and so the probability of detecting a particle in detector 1 is then given by this quantity plus this quantity squared, 4 times the probability of scattering at 90 degrees, or twice the classical result. On the other hand, if we had fermions, we had to take the minus sign, and in that case, the probability of a particle appearing in the detector is just at 90 degrees. But that's just 0. So we see here some very distinct predictions depending on the nature of the particles. If the particles are distinguishable particles in some way, then the probability of scattering into the detector is just the probability that one scattered into the detector or the other. In other words, it's twice the probability of any one scattering event. If, however, the particles are bosons, we get twice the probability for scattering at 90 degrees. So by making the particles indistinguishable, we now observe an anomaly in the scattering experiment that scattering is enhanced at 90 degrees. On the other hand, if the particles are fermions, we get the amazing result that there is no scattering at all at 90 degrees. An alternative statement of this is the Pauli exclusion principle. If you realize in the 90-degree scattering experiment the final state of both particles is the same, what we've just worked out is that for fermions, the probability of finding them in the same state is 0. Let's look at this another way. In general, if we have a state psi1, which could be occupied by particle 1, and a state psi2 that could be occupied by particle 2, then in quantum mechanics, if the particles are indistinguishable, we cannot tell that apart from a state psi1 occupied by particle 2 and a state psi2 occupied by particle 1. And then our only task is to add those two combined probabilities together, but bearing in mind they might be fermions or bosons, we'll have to use a plus or minus sign. So what about when psi1 equals psi2, like scattering at 90 degrees? Well, then in that case, if we take the minus sign, we see that we have which of course is 0. So the probability of finding two particles in the same state in quantum mechanics is 0 if they are fermions, and this is the famous Pauli exclusion principle. What makes a boson or a fermion? This is a profound point. It turns out to be connected with the spin of the particle, this quantum mechanical quantity that we referred to before. Spin is quantized in units of Planck's constant. Particles that have half-integer spin, like electrons for example, are always fermions. In the case of nuclei, the situation is more complicated. Nucleons have half-integer spins, but nuclei have different number of nucleons which combine to give a total spin for the nucleus. So for example, helium-3 with 3 nucleons has 3/2 h-bar spin, and it is a fermion. Helium-4, adding 1 more nucleon, has integer spin, and it is a boson. So these two nuclei have completely different physical properties. And that's manifest, for example, in the existence of superfluidity in helium-4, but not in helium-3.